Welcome, math lovers, to another problem from the channel Solutions from the Book. This time we have selected a very interesting problem, a geometry problem actually, and which has been taken from the first ever Junior Balkan Mathematical Olympiad of 1997. This JBMO, as they call it, is a math competition between the countries of the Balkans, but there are also some unofficial invited countries to this competition. And the students which participate in this Olympiad must be at maximum of an age of 15 and a half years old. So as I said, this is the first ever problem which has been given on the Junior Balkan Math Olympiad. So let's go through it together. The problem states that 9 points are given inside a unit square, a square with side equal to 1 centimeter. Prove that 3 of these points are the vertices of a triangle with area smaller or equal to 1/8 centimeter square. As always, please pause this video if you want to try to find a solution by yourself to this problem. I guarantee you that it is a very lovely problem, so it is a very beautiful problem. So please try to find a solution, and at the end, please write down on the comments if you find some solution to this problem, so we can make a comparison to the one that I'm going to present to you right now. We go directly to the solution of the problem that I have prepared. Of course, I have hidden the problem solution in order for us to go through it step by step together. And let's start. First of all, I must say that in order to solve correctly, let's say, geometry math Olympiad problem, you have to do a very good figure of the problem in order for things to be clear and to be, let's say, concise during the marking of the problem if you are a participant on math Olympiads. Of course, we start by making some definitions. Let's call the square that has been given to us the square ABCD. The problem conditions give that sides AB is equal to BC is equal to CD is equal to DA equal to 1 centimeter. The area of the square is, of course, 1 by 1 is 1 centimeter squared. So, in order to start the solution of this problem, we know that we are given 9 points inside the square, so inside or on the sides of the square. So, inside the square or on the sides of the square, and we should prove that that 3 points from these 9 given points inside the square can form a triangle with area less or equal to 1/8 centimeter square. So first of all, our solution starts by dividing the square, the given square ABCD, into 4 smaller squares with sides equal to half a centimeter. So ABCD will be divided in mini squares AEFG, AEFG, EBF, this square over here, this square over here, and this square over here. We have concentrated our effort on square AEFG in order to give the solution to the problem. So by dividing the square into 4 smaller squares, we will have that the area of these 4 smaller squares is equal to half centimeter by half centimeter, 1/4 centimeter squared. But now, by the pigeonhole principle, which many of you might know, or the Dirichlet principle as they call it, given that there are 4 squares and 9 points which are inside or on the side of the big square, this means that one of these squares will contain at least 3 of the 9 points, because every square can contain a maximum 2, 2, 2, and 2, which give 8. So at least one of them must contain at least 3 points. So let's suppose that inside the square, the mini square IEFG, we have 3 of the 9 points, and let's call these points M and P. So these 3 points, M and P, will form the triangle M and P. And we will try to prove that the area of this triangle is smaller or equal to 1/8 centimeter square. In order to do so, in the triangle MNP, from the point N, which is between the points M and P, and in front of the side MP, we draw a parallel line to the side AG. So from N, we will draw this parallel line to AG. The parallel line to AG intersects the side MP on point S. So we will have that NS is parallel to AG. We now will draw the perpendiculars from the other points of the triangle, from point M and from point P, toward the line NS. We will call the foot of the perpendicular from M H, and we will call the foot of the perpendicular from P R. So we will have that MH is perpendicular to NS and PR is perpendicular to NS. Now, in the triangle M and P, we will have that the area of triangle M and P is equal to the area of triangle M and S plus the area of triangle NPS. But we know that the formula for the area of a triangle is equal to base times altitude. So for the triangle M and S, the area will be equal to NS times MH, while for the triangle NPS, the area will be equal to NS times PR. So by doing these substitutions on the formula area triangle MNP equal to area triangle MNS plus area triangle NPS, we will have that NS times MH, which is the area of MNS, plus NS times PR, divided by 2, of course, is the area of triangle NPS. So we factorize NS, that we will have that the area of triangle MNP is equal to NS times MH plus PR, which are the altitudes from points M and P toward the line NS, which is parallel to AG. So let's call this first expression we got up here as expression number 1, equation number 1, and we go forward with the proof of our problem. Now, we know that NS is of course smaller or at maximum equal to AG, because points M and P are inside or on the sides of the triangle AEFG. So this means that NS is smaller or equal than AG, and MH plus PR, the sum of these two altitudes, is smaller or equal to FG, which is the other side of the smaller square AEFG. So by making these substitutions into the expression that we got up here, the expression number 1, it becomes that area of triangle MNP, which is equal to NS times MH plus PR, is smaller or equal, NS smaller or equal to AG, and MH plus PR is smaller or equal to FG. So AG times FG divided by 2. But AG and FG are the sides of this mini triangle, which we up here said that are equal to 0.5 centimeters. So we will have that 1 divided by 2 multiplied for 1 divided by 2, all of these divided by 2 is equal to 1/8 of centimeter square. So we just proved that the triangle MNP has area of maximum smaller or equal to 1/8 centimeter square, which is the let's say the request of this problem. So area triangle MNP is smaller or equal than 1/8 centimeter square. But now, for the remaining part of the solution of this problem, we have to determine when does equality occur. So when does the area of triangle MNP equal 1/8 centimeter square? So in order to do so, we see that the equality is only reachable when NS is equal to AG and MH plus PR is equal to FG. So NS equal to AG and MH plus PR is equal to FG. In order to attain and to obtain this configuration, we say that point N must be on the side AE, while given that MH plus PR should be equal to FG, we say that the points M should coincide with point G, so point M should be on the point G, and the point P should coincide with point F. So we are given that in order to obtain the equality, point N must be on the side AE, and it can move from A to E, so it can be, let's say, it can obtain a position from point A from point to point E, but point M should be, let's say, should coincide with point G, and point P should coincide with point F in order for MH plus PR to be equal to FG, while point N can move in the segment from A to E. So the equality is only reachable with these conditions. So point M and P must be fixed, and point N can move from A in the segment AE. So this is the solution that I brought forward regarding a very interesting and very nice problem, in my opinion. So please, if you have any other solution for this problem, don't hesitate to write it down in the comments. In the meanwhile, thank you very much for watching the videos of our channel, and please like and subscribe if you would want to watch similar videos in the future. Thank you for your time, and bye.